Hello, I'm Dr. Abhishek Sharma. In this video, I will discuss the extension of noise for frequency modulated systems, pre-M phases and D-M phases. So let us start the noise in pre-M phases and D-M phases for the frequency modulated systems. As I have already discussed in the previous videos that this is the simplest block diagram presentation of a frequency modulated system. In this figure, the first part is the transmitter section. This is the channel part where noise NT is inserted with the power spectral density equal to eta by 2. This is the PSD of the noise. This was the transmitter. This is the receiver section, which is comprised of amplitude limiter, a differentiator, envelope detector, and a low pass filter. I've calculated the noise input after the high pass filtration, that Ni, which is the noise power, is given by 2 eta and Fm, and at the output of the low pass filter, the power spectral density at this point is given by k square upon a square, that is AC square, S of n q and omega dot. So this is the power spectral density at the output of an LPF for this system. So from this expression, it was clear that the output power spectral density is proportional to the frequency square, right, which is the modulating frequency. Now you can note that S of nq omega is equal to eta for mod of omega, which is less than or equal to, which is your omega m. This will be 2 into Fm into pi, that is equal to omega m. The power spectral density Snq of omega is equal to eta for mod of omega less than or equal to omega m. This was proved in the previous videos that S of nq omega will be plotted as this is your power spectral density. This will be minus of omega m and this will be plus of omega m. So at the output S n naught omega, it will be equal to k square upon AC square into omega square into S nq omega. So that will be equal to k square upon AC square into omega square into eta, and that will be also valid for mod of omega less than or equal to omega m. Now as S of n naught omega is equal to k square upon AC square omega square into eta for mod of omega less than or equal to omega m. From this expression, we can clearly see that the power spectral density of the noise at the output is directly proportional to the message frequency, right? So this relation is a parabolic relation or a non-linear relation between power spectral density and the frequency term. So if I want to plot this power spectral density with respect to the frequency, I will definitely get a parabolic relation in the diagram also. So it will be presented as, right, so this is your frequency and this term is your S of n naught omega, and this is valid from minus of omega m to plus of omega m. So we can also write this S n naught omega as, so we can also write S of n naught omega mathematically k square upon AC square into omega square into eta for mod of omega less than or equal to omega m. Elsewhere it is 0. As the power spectral density at the output of the filter has a parabolic relation between the frequency and PSD. So there is another conditional effect generated in the frequency modulated system, which is known as noise quitting effect. Now we know that the power spectral density at the output is given by Sn naught omega, that is equal to k square AC square omega square into eta for mod of omega less than or equal to omega m. So we can obtain the noise power as equal to 1 upon 2 pi integral minus omega m to omega m k square upon AC square into omega square into eta into d omega. So this is from the Parsifal's equation, where you can calculate the power is equal to 1 upon 2 pi integral from minus infinity to plus infinity, and then you will replace power spectral density here and d of omega. Now the noise value will be equal to 1 upon 2 pi from k square upon AC square. You can take this from the integral, you can take it as a common term, and eta as well. So it will be omega to the power 3 divided by 3 for minus of omega m to omega m. So that will be equal to k square eta divided by 2 pi AC square into omega m to the power 3 1 by divide by 3 minus of omega m to the power 3. So this will be n naught is equal to k into eta divided by 6 of pi AC square. So that will be 6 of pi AC square into twice of omega m cube. So that will be equal to k square eta into omega m to the power 3 divided by 3 pi into AC square. Now we know that the carrier signal power for the frequency modulation is given by AC square by 2. So we can take this value AC square by 2 divided by 2. So we will get n naught is equal to k square eta omega m to the power 3 divided by 2 divided by 3 pi into power of carrier signal. So noise power will be approximated as equal to, it will be again k square approximated as divided by 6 of pi into maximum frequency contained. This is the maximum frequency of FM bandwidth to the power 3 divided by the carrier signal power, right? So finally we can conclude that the noise power is proportional to the maximum frequency of FM, its bandwidth of, you can say, message, right, whole divided by the carrier power. So if I want to suppress the noise power, then definitely I have to increase the carrier power. So that's why this is the important point. So if you want to suppress the noise power at the output of the receiver, then you have to increase or you have to transmit more carrier power. This is the one way, right? And the ways you can clearly see that you have to reduce the bandwidth of the message. So if you are sending a good quality of message, then definitely the bandwidth of the message, actually you cannot compromise with the bandwidth of the message, right? So the carrier signal, there should be a trade-off between the carrier power, noise power and bandwidth of the message, right? From the above expression, I will write it as, from the above expression, it is clear that if we increase carrier power, the output noise power decreases. This effect is known as noise quitting effect. This effect is very important for the noise analysis in frequency modulated systems. So the noise power and the carrier power are both interrelated. When you increase the carrier power, the noise power at the output of the frequency modulator's receiver will be decreases. Now the spectrum shape of Sn naught omega shows a parabolic nature, right? So I have shown this one. So this is a parabolic nature, parabolic relation between the power spectral density as well as the frequency. Suggests that the maximum frequency content of message bandwidth faces the maximum noise. That means as power spectral density increases with respect to the frequency in a parabolic nature, so you can see that as PSD is increases, that means with respect to the frequency, noise power will be also increases, right? That means when omega increases towards omega m, so suddenly the noise power will increases rapidly with respect to this frequency omega. So you can clearly see one important thing here, that for lower frequency content, the noise power is very low in comparative to the higher message frequency content. That means the noise behavior for different frequency components of the message will be different. Low frequency will face low noise and high frequency will face the high noise. That's why I'm saying that the parabolic nature suggests that the maximum frequency content of message bandwidth faces the maximum noise. That means as the frequency increases, the noise power also increases. So this noise affects more on higher frequencies in comparison to the lower frequencies. So we have to arrange, or we have to mechanize some circuitry that will actually just reverse this process. So such type of circuitry is considered as pre-emphasis, and its inverse system is considered as de-emphasis. So to compensate this effect, we use pre-emphasis, as I've already told you, circuit at the transmitter and before modulation. So first what will happen, I will take the message signal, then after that pre-emphasis filter is used, and after that the message will be passed through the frequency modulator, where frequency all the modulation process will be done, and after that I will transmit the frequency modulated signal with the help of the antenna. So pre-emphasis basically enhance the amplitude of higher frequencies in comparison of lower one to minimize the noise effect on higher frequencies. Now if we consider the circuit of the pre-emphasis, it is simply a high pass filter with the frequency response mentioned in this figure right here. So you can clearly see that the magnitude response with respect to the frequency, or you can say the CTFT of this pre-emphasis circuit, is simply a high pass filtration process, right? So in this process you can clearly see that I'm just increase the magnitude of the higher frequency component with respect to the lower frequency component. Why I'm doing this? Because higher frequency content in this case, when our message will pass through this filter, the magnitude of this higher frequency will be increases, and in comparison to the lower one. So that's why this pre-emphasis circuit is very important. So it will just neutralize the impact of this parabolic behavior of noise power with respect to the carrier power. So this is the pre-emphasis circuit, this is the resistance R1, this is R2, and this is the capacitance. So this is basically high pass, or you can see the differentiator. Similarly, de-emphasis circuit is used to nullify the effect of pre-emphasis at the receiving end. So when we use de-emphasis circuit after discriminator, so like this is actually pre-emphasis circuit, so it's just reverse circuitry will be the high pass filter definitely. So this is the high pass filter. So at the receiver end we will use the de-emphasis, that will be the low pass filter. So transfer function is of this is the pre-emphasis transfer function, and this is your de-emphasis circuit, right? So receiving end, this is the resistance, simple resistance, this is the capacitance. So at the receiving end, this is the resistance, this is the capacitance, and you are just applying the demodulated input here, and you will get the output. So you can clearly see that this is the magnitude response of this de-emphasis circuit, which is the low pass filter. You can actually see that. You can clearly see that this will just reverse the what we have done at the transmitting end. It is increasing the power of the lower frequency content in comparison to the higher frequency content. So this is the transfer function of the de-emphasis. So for a same and demodulation system, the relation between the pre-emphasis and de-emphasis, or you can say the relation between the transfer function of pre-emphasis and de-emphasis is given by this equation. So the multiplication of these two transfer functions will be a constant. So that is very important, because when we apply pre-emphasis and de-emphasis for a certain frequency modulated system, the relation between the pre-emphasis and de-emphasis should be such that multiplication of the transfer functions of these two filter system should be a constant. So in this video, I have described the noise behavior with respect to the carrier signal, noise squirting effect, and the circuitry, which is the de-emphasis and pre-emphasis for the frequency modulated systems. So in this video, that's it. Thank you very much.